Welcome students. This is Equilibrium part 3, the quest for a never-ending case. Now why I have named it never-ending case? Because the reaction neither goes completely to the right nor completely to the left, but stays somewhere in the middle. And the products may be more, maybe less. The reactants may be more, maybe less. But the reaction proceeds in two ways, that is in opposite directions. So keeping the concentrations of products as well as the undissociated reactants or unreacted reactant molecules constant at equilibrium. Under given circumstances, of course, of temperature, pressure, volume, and other parameters to which it is subjected. Ionic equilibria is the topic that we are going to discuss today. It deals with solutions of weak electrolytes and also gases. Weak electrolytes do not ionize to a large extent, and an equilibrium is reached where we have undissociated reactants, undissociated reactant molecules, and ions of the products as well. Maybe the molecules of the products as well. The concentrations of the constituents of an equilibrium can be quantified. In the equilibrium set up by weak electrolytes, the concentrations of the products are far too low. And that's why they are called weak electrolytes. The Kc equilibrium constant, now here we will call it dissociation constant. The Kc value of the equilibrium of strong electrolytes approaches infinity. It is difficult to work with infinity. Due to complete dissociation in an aqueous solution, the strong electrolytes do not set up an equilibrium. Ostwald's dilution law. The degree of dissociation is a measure of how much a substance breaks down into smaller units such as ions or radicals when it is in a solution or a gas. Both are applicable. Both are applicable. Solution or gas. And we have two examples at the end of the video to show you that this does happen. The degree of dissociation is usually represented by the Greek letter alphabet alpha, and it can range from 0 to 1. A degree of dissociation of 0 means that substance does not dissociate at all, while a degree of dissociation of 1 means that the substance completely dissociates into its smaller units. So for weak electrolytes, the value ranges between 0 to 1. If it is approaching 1, the products are more. If it is close to 0, the products are less. That means dissociation is very, very, very less. Alpha is expressed in decimals or percentage. Decimals or percentage. In either way we can express alpha. So the extent to which a given electrolyte dissociates in its aqueous solution is given the value of alpha. In short, the value of alpha tells us the extent of dissociation of the given electrolyte, which is weak in nature. We continue with Ostwald's dilution law. Let alpha be the degree of dissociation of A in its aqueous solution. This is AB. And the general equation is given as AB aqueous, reversible, B plus and D minus. B and D are two different things. It should have been A. We can consider A also. We can consider B also, because there is AB. So it will dissociate into A plus and B minus. Nevertheless, at equilibrium, we have 1 minus alpha. Remember, 1 mole of AB is giving 1 mole of B and 1 mole of D. If this is a complete dissociation, 1 mole of AB will give 1 mole of A and 1 mole of B. Therefore, if only alpha molecules dissociate, then we will have alpha moles of B and alpha moles of D. Concentration at equilibrium is C into 1 minus alpha, which is C alpha and C alpha. Now, if we calculate Kc, that is the equilibrium constant of concentration, here it is known as dissociation constant. This is known as dissociation constant. Kc is equal to C alpha square, because C alpha into C alpha divided by C into 1 minus alpha. So this, upon cancellation, gives us C alpha square. As you see, this will become C square. This will become C square alpha square. So 1C from here, and the square also goes to C alpha square. And alpha, as it is much less compared to 1, it can be neglected in the denominator. Therefore, we have alpha equals root over Kc by C. Now, since concentration is 1 by volume, we can write the equation as alpha equals root over Kc into V. This is Ostwald's dilution law in mathematical form. The Ostwald dilution law states that the degree of dissociation equals to the root of the product of equilibrium concentration and volume of the solution. So this is in words, and this is in mathematical form. This also can be written, both can be used wherever and whatever is given in accordance with that. Applications of Ostwald's dilution law or Ostwald dilution law. It is helpful in determining the strength of weak acid or weak base by measuring its degree of dissociation at different concentrations and calculating its dissociation constant and its pH value also. Estimating the solubility of a sparingly soluble salt by assuming that it behaves as a weak electrolyte and applying Ostwald's dilution law to its saturated solution. Color changes in acid-base indicator. Studying the effect of temperature, pressure, and ionic strength on the dissociation of weak electrolytes by observing how these factors change the dissociation constant and the degree of dissociation. The dissociated ions may get hydrated by water molecules solvated, so the weight is altered, the concentration of the ions. If it gets solvated, it increases in weight, and the concentration of ions, you see, may rise or fall because the size becomes large. So the Ostwald dilution law in its simplest form, as we are studying right here, will not apply to those cases. Let us see some numericals. A weak acid HA is 3% dissociated into 0.1 m molar solution. This is concentration. C, the value of C in this numerical is 0.1. Calculate the value of Ka. K is the dissociation constant of the acid. If I use Kb, it will be dissociation constant of a base. So two constants are subscripted as A and B. Now solution, 3% is equal to 3 divided by 100 is equal to 0.03. The equation for dissociation is as follows: Ha in aqueous, reversible H plus aqueous plus A plus aqueous ions. Moles at equilibrium, applying the value of alpha, 1 minus 0.03 of Ha, 0.03 of H plus, and 0.03 of A plus. The reason is that suppose if 1 mole of Ha dissociates completely, I will have 1 mole of H plus and 1 mole of A minus. Therefore, continuing with the same criteria, if only 0.03 moles are getting dissociated, I will get 0.03 moles of H plus and 0.03 moles of A minus. Concentration at equilibrium, concentration is 0.1 m into 1 minus 0.03. This is 0.01 into 0.03, and similarly 0.01 into 0.03 for A minus. Calculating the value, this into this is 0.01 square into 0.03 square, that is C alpha square, divided by 0.1, this is 0.1 into 1 minus 0.03, which gives us 0.1 into 0.03 squared divided by 1 minus 0.03, which is 0.97. Expanding this, you can use your calculators. You will have 0.00009 divided by 0.97, and this works out to be 9.28 into 10 to the power minus 5. I hope you understand. You can calculate either using log tables or calculator. The calculator will do it very fast for you. Another type of sum which I took from an NEET paper is this. Carbon dioxide is 2% dissociated at equilibrium according to equation 2CO2 reversible 2CO plus O2. Find the mole fraction of carbon dioxide at equilibrium. Now this brings in a little bit of the first chapter where you study some basic principles of chemistry. So there we have a discussion on mole fraction. Mole fraction is, for your purpose and convenience given here, moles of the compound that we are asked to find out divided by total number of moles. So here also 2% is equal to 2 by 100 is equal to 0.02. So moles at equilibrium, 1 minus 0.02. See, if I take 1, I am using alpha. If I take 2, I have to use 2 alpha. So to keep the calculations simple, we use 1. Whether it is 1, 2, 3, whatever it is, we take 1. And then fit in the values according to the coefficients here. So it is 1 minus 0.02. This will be 0.02. And this, you see, between this and this is half of this. So it will be 0.02 divided by 2. Therefore, total number of moles at equilibrium are 0.98 plus 0.02 plus 0.01. And this is 1.01. Therefore, mole fraction of CO2, applying this formula, total number of moles is 1.01. Number of moles of the compound whose mole fraction is asked is 0.98, and 0.98 divided by 1.01 is 0.97. So mole fraction is 0.97, which is very close to 1, and therefore the dissociation is very, very less, as it is indicated by this 2% value. Thank you and have a nice day. I'll come up with the solution of some more problems and help you in continuing your quest for the never ending, that is chemical equilibrium. Thank you and have a nice day.